So I welcome you back to the section on mathematical physics. It's a great pleasure to introduce Yuval Ne'eman. As some of you may not know, Yuval is an extremely well-known physicist. He was with Murray Gell-Mann in the 1960s, one of the two people who invented the SU3 symmetry as the fundamental symmetry of particle physics, and is known in this country for work also in other domains, which I will keep secret. So he will talk today about physics as geometry, Plato vindicated. Yuval Ne'eman.
Turn it on. Now you hear me. Well, the idea being that since we are now, this conference is supposed to deal with vision, so vision into over large distances, I assume that the idea is into the future, but it's easier to look into the past. So, and the excuse can be extrapolation. If you can look over large distances into the past and see things growing, then you may be able also to make some better guesses, or at least it's a way of making guesses about the future. In particular, because in the examples that I'll show, there have been people who have made guesses that turn out to have worked over 2,000 years, or almost 3,000 years. And these guesses somehow came out right in our century. So I'm going to stress these examples. That's why I mentioned Plato as being vindicated by the 20th century. There's no question that the physics of the 20th century, the fundamental physics, have become geometry. And we have, there is a quote from Plutarch. Anybody doing mathematics or physics should be able to understand that. It's any mathematician can read Greek. I remember in Greece, I was looking at in the elevator what to press, and it said isogeon. So it's so clear once you know science or mathematics. So it's Plato or Platon, as should be pronounced. Platon. Elegium is like alleges in English, like also an elegy, but anyhow, that's the root. So Plato alleges that theon, like that's God, like in theocracy and atheism. Theon, is really like aeons, that means forever. That God forever geometrizes, geometry. So that's what Plutarch says that Plato used to say. Nobody knows why he said it and how he got into that kind of conclusion, but that's really what you want us to do now and look into the future. So I'll try to look mostly into the past, and then maybe we can extrapolate a little bit. Why do I start with the Greeks? There was scientific activity earlier, but not in the sense that we have in mind when we speak of science now. That means a way of an assumption that nature can be understood per se by finding out some rules and by logical conclusions from these rules derive everything else in nature. That assumption is really, that starts in the 7th century in Greece, 7th century BC in Greece, and achieves fantastic results already in Greek times. I decided, for the sake of economy of time, I tried to think of ways of abstaining from telling you stories, but nevertheless, I think I have one or two stories that I won't be able to not to tell, because they're too good also in terms of the lessons that we can derive from them. Well, when I say that Greek science got to excellent results, I want to make a distinction between two things, between Greek science, physics, and Greek and science in general also, of course, mathematics, because the first science that was really developed in the sense that we give now to a science is geometry. And that was really Greek geometry. When you get to Euclid, is as perfect as anything you'd like to do nowadays. But there was also Greek metaphysics, not in the sense that we give to metaphysics now in terms of things which are nebulous, etc., but ideas like this idea of Plato about geometry, which must have come from either some deep intuition or understanding of things around them, but which were very vague ideas, could not be turned into actual results at the time. But the example is really atomism. Take Democritus of Abdera, coming up with developing the idea of atomism. It took all the way to John Dalton in the end of the 18th century and the beginning of the 19th century. The story is unfinished because we really have now, we've gone down from atoms to nuclei and to particles and to quarks and so forth. So if you are a good Marxist, or at least a Leninist, then there is a saying of Lenin that used to be quoted in the Soviet Union often in order to protect the particle physics, because Lenin said that when the electron was discovered, that you see that that's not the end of the story, and the idea is that the electron is still made of further particles and so forth. That's part of it was also copied in China in Mao's teachings, that was called stratons, that you go by levels. But still, the idea is already there at the level of Democritus, and that's one of the two stories that I decided not to banish away from this lecture. Democritus of Abdera. Abdera is somewhere in Turkey, in Europe now. It's not far from Edirne. And Democritus was from one of the richest families in Abdera. And he was interested in physics, and he decided to go to Egypt to study in Egypt. So he spent a lot of money going to Egypt, stayed 7 years to studying under the Egyptian masters, then went to Babylon, stayed 5 years there, all the time spending his family's money studying under the Babylonian masters, came back to Abdera bankrupt. The Senate of Abdera, before whom he gave a talk, were so impressed by Democritus' ideas about atoms that they voted for him to get 400 talents of silver, which the Encyclopedia Britannica 13th edition says is equivalent to $1 million. That's around 1920. So nowadays it would be 10 million or 20 million, I don't know, something of that nature, so that he should not have to worry until the end of his life, and would be able to develop with his students these ideas. Compare with the US Senate closing down the accelerator in Texas several years ago. I put that in the second edition of my book, The Particle Hunters. I added that part and that story at the end of the book. Coming back then, so I make this distinction between the physics, or science, and metaphysics, which are these general ideas like that idea of atomism. On the scientific side, take the results, for instance, Archimedes' law of buoyancy, or his understanding of angular momentum. I mean, just the question of the lever. Or if you let's take the results in astronomy. Well, finding out first of all that the Earth is round, and then Eratosthenes. That's 3rd century BC. He was from present-day Libya, from Cyrene, and he became a professor at Alexandria. and he measured the radius of the Earth with a precision of 0.5%. He did it by, that's the beginning of my second story, before we get down to more serious matters. He did it by, suppose this is Alexandria, this is Alexandria, and this is Siena in southern Egypt, Aswan. He knew that on a certain day of the year, the sun is in the zenith in Aswan. He verified it, and then he had somebody to check that it was happening at that time, and he measured the angle to the sun in Alexandria. So he measured this angle. So he had this angle, which is this angle, and knowing the distance between Alexandria and Aswan, which was very well known because Egypt was already an organized kingdom for 3,000 years, and the king's messengers had gone back and forth, Pharaoh's messengers, and so the distance was very well known. He got the radius of the Earth with a precision of 0.5%. At the same time, well, 100 years later, Posidonius, who was the head of the school in Rhodes, which was a good place, a good research place, because another astronomer, Hipparchus, in Rhodes, measured the distance to the moon with a precision of 1%. But Posidonius repeated this measurement, and but he did it differently. He took Rhodes and Alexandria as the 2 points, and not the sun. There is, in the southern sky, there is a star, Capella, which is on the horizon in Rhodes, and which has an angle of elevation from Alexandria. And that's how he calculated things. First he got a result similar to Eratosthenes's, but then he verified with various seamen, various captains of various ships, what the distance between Alexandria and Rhodes was, and they varied in opinion, and finally he selected a certain distance, which gave him a radius of the Earth which was 60% of the correct radius. Ptolemy, who was the man who wrote the review afterwards, Ptolemy thought that because Posidonius' result was later than Eratosthenes's, it must be more correct. And so Ptolemy included the result of Posidonius, the wrong result, which was 60% of the correct size. Columbus had Ptolemy's book. So Columbus, when he presented a proposal and he wanted a lot of money because he wanted the state to give him 3 ships, and that was something in the budget, all of that for research, etc. So he explained that he calculated and showed that, and he was using these data, that the distance to India would be closer going that way than the usual way that the others were going. Therefore, there would be lots of money saved over the transportation, and so in the import of spices, which was the main business, and the royal treasury was also getting its share in that. So there would be a lot of money saved. So it was a good proposal in terms of showing that it was worth investing the money because there would be some direct outcome, and that was his proposal. The treasury gave it to the professors in Salamanca, at the University of Salamanca, to check. These included Avram Ibn Zakuta, for those who know who that was. Anyhow, the professors of Salamanca knew the correct results because they had studied both Eratosthenes' results and Posidonius's. In 2,000 years that had passed, almost 2,000 years, the Genoese and the Venetians had mapped the Mediterranean in a very precise way, so they knew that the correct result was really Eratosthenes' results. So they gave a bad referee report saying, no, it's nonsense. Nobody will ever go to India in this direction. It's much further away. It'll take Columbus 6 months and not 3 months to get there. And it will be also a catastrophe because he can't take supplies for more than 3 months. So it was a completely negative report. Columbus had connections, and somehow the proposal was nevertheless okayed, and he went there. a question that now, one more remark about that before we go on. About 5 or 6 years ago, there was a film on Columbus in which Columbus was played by Gérard Depardieu. And this dishonesty of the filmmakers is terrible. First of all, the professors of Salamanca were made to say that the earth is flat. Only Columbus knew that the earth was round, and they kept saying that the earth is flat. Second thing was that Columbus Depardieu was all the time saying, I want to find new words, whereas the true Columbus died still thinking that he had found a way to India. So, now, I suggest that for the question period, you think about what would you have said as referees from Salamanca, because after all, America was discovered. So would you have missed that or not? And think about that question. Anyhow, that's as far as the non-mathematics part of this conference, of my talk goes. I couldn't refrain from telling that story. Now, I have added, I thought about it, well, on the geometrization of physics in the 20th century, you can find two papers that, one is in the 40th anniversary of the IHES. I have a paper about that. And another one is in a conference on functional differential equations. You can get the reference on that. So I decided to add one more topic here. And this topic is, I added it because I found that really it also connects with those things that we were discussing, or that were done, general ideas in Greek times. Let me, perhaps, I'll show you, in order to explain that point. I looked up this morning what the American Heritage Dictionary was saying about Pythagoreanism. And that's what the definition was. The syncretistic philosophy expounded by Pythagoras, chiefly distinguished by its description of reality in terms of arithmetical relationships. That's in the dictionary. Now, this really happened in the 20th century, this thing. And why did it happen in the 20th century? That's what I'm going to explain. So I have 2 points here. One is the geometrization, and the other one is the Pythagoreanization, or you could also call it, I used first the term musicalization because Pythagoras got it from music. That's really the idea of the music of the spheres and so forth. And but that's, I think I just found a better term, maybe harmonization, or it's really the harmonics that play the role, because that's where Pythagoras got his idea. He got it from the music, in which was one piece of physics that they had understood. And they knew that they had the harmonics, and they had these very simple arithmetical relationships. And so for that, you need certain conditions, and they happened in the 20th century. So now let's go methodically. So 5 ideas in Greek metaphysics that I mentioned already: the atomicity, the musicalization is what I say about what I said now about Pythagoras. There is another idea which relates to something that was mentioned by Professor Freulich an hour ago, and this is the question of friction or not, no friction. Plato had the idea of a vacuum. He believed that that was an interesting concept. Aristoteles negated that completely and said that nature doesn't tolerate a vacuum, it doesn't exist. He was one of these physicists who think of effective physics. So, and the true physics has always some friction. So he developed physics with friction. That's why Aristoteles comes to the result that force is proportional to velocity, not to acceleration in his case, which is correct. If you have friction, then you get you calculate the velocity of a stone falling into the water, and you find that it's proportional to the weight of the stone. And so, but Plato believed that there has to be, that the vacuum has a meaning, and it was really only vindicated when Galileo, at least if you think that throwing things down from the Tower of Pisa, they really get at the same time downstairs, then there must have been some kind of imagination, imagining that it's a vacuum and understanding that it's because of air resistance that they don't come precisely at the same time to the ground. They don't reach the ground. But anyhow, we know now that without the vacuum we couldn't have Newton's laws and so forth. Geometrization, which is one of the things I'm going to discuss, and the other idea which here I want to give back to Aristotle, that's Aristotle, what is due to him. We have a very terrible image of Aristotle because of what the church did to him by canonizing part of his writings, and they became, for 1,000 years, something that you couldn't touch, and they became dogma. But that was not his responsibility 800 years earlier, when he had these ideas. He invented the variational approach, the variational method. And so for that he certainly deserves credit. From him, you can, well, already in Hero of Alexandria, which is about 200 years later, has a proof that the angle of, in optics, that the angle of reflection is equal to the angle of incidence, based on Aristotle's variational principle, because we all learned that Aristotle believed that said that everything has to move in circles. That's nonsense. He doesn't say it. What he really says is that he observes that things move in circles. It's not a bad approximation. If you look at the planets, the orbits are not that different from circles. And he explains that by a variational principle. He says that they move in a straight line because the straight line is the shortest route. They move in a circle because the circle is the contour. For a given contour, it contains the maximal area. So he has this kind of approach, which is based on a variational approach, and that leads from Hero to Fermat to Leibniz, etc., and I won't touch that anymore. Now we'll concentrate on geometrization and musicalization, these things that happened really in the 20th century. And it was not a matter of the theorist wanting to use geometry or musical approach, or it was really nature that made that decision. That's what I'm going to try and show. The geometrization. That came in two phases. The first phase was starts with special relativity and special and general relativity. That's really between 1905 and 1915 or 1920. You have phase one. It goes like that. When Einstein writes in 1905 his paper on the one that gave relativity, which is on the electrodynamics of moving bodies, he has no idea that he's doing geometry. There's no trace of geometry in what he's saying. He's really calculating using Maxwell's equations and looking at the symmetries of the equation and checking what happens to fields when the charged bodies move. It's Minkowski, his former teacher at the ETH, who in 1908, at a talk in Cologne to the Association of German Physicians and Nature Researchers, there was such an association, he explains that what Einstein has found is really that the world has a Minkowski metric. That's what we call now a Minkowski metric. That means that it's a pseudo-Euclidean. It's not a direct product of an R3 times an R1. It is really a pseudo-Euclidean geometry that affects everything. And so this is really Minkowski's 1908 contribution. Now, Einstein was already involved a year earlier in working out using special relativity and the old quantum theory, following his success with the photoelectric effect, thinking of E equals h bar nu, that means the frequency representing the energy, and making the assumption that gravity is really a coupling, if you call it a coupling to the mass, which was Newton's gravity, then it's really E over c squared. The square I forgot here, at least my computer didn't put it in, so put the square there. So it's really E over mc squared. That means h nu over c squared. And he calculates and he gets a deflection of light, which is, if you make the calculation, you find that it's half the deflection of general relativity, not a bad approximation. But it's terrible for him, because it means that the way he presented special relativity as the idea that the velocity of light is the sacrosanct object, the real invariant of nature, suddenly the velocity of light becomes something that can vary because of gravity. If you are in a gravitational field and you have an acceleration and you curve, you deflect light. And just at that time, he gets this gift from Minkowski of the geometrical interpretation. And he has his colleague, Marcel Grossman, who helped him out. Well, the whole family helped him out. The father of Marcel Grossman got him the job at the patent office in Bern. And when he was refused the job of an assistant at the ETH, and here Marcel Grossman tells him that this is really, he asks Marcel Grossman what is the meaning of a metric in which somehow the metric varies, and Grossman explains that that's Riemannian geometry, and you have from that point on the route to general relativity pointed out. So that's where geometry surreptitiously first entered physics, through this completely unexpected development. Before I leave here this topic, I want to mention Einstein for years and the whole physics community, not the whole, I would say more the astronomical and the astronomers and a few physicists were very interested in extending general relativity so as to include also Maxwell's theory. Continuing, since general relativity had unified the gravitational force with inertia, here there was room for another unification. And so you have immediately from 1918 roughly to 1920 and something, you have all kinds of suggestions about how to fit in electromagnetism. It's very interesting that was always considered, I know when I entered physics, it was considered as a waste of time by Einstein and others that had spent their years working on the unified field theory. It turns out to have been one of the most useful things you can think of, because the second geometrization that I'll explain in a few minutes is entirely based on the results of that period. On the one hand, you had Hermann Weyl, who wanted to put in electromagnetism as what we call now a fiber bundle or a gauge theory. And that means a base space, let's say horizontal base space, which is space-time, and at every point of space-time a fiber, which is a group or a representation of a group, which is already a vector bundle. And he used the wrong group to start with. In 1918, he was using scale invariance, and there were problems with that. But then by 1928, there was already 25, there was Schrödinger's equation, and Fritz London showed by 1928 that the electromagnetism was really invariant under the change of the phase in the Schrödinger equation. And so Weyl said, well, I can put that into my theory, make the phase locally dependent, a different phase at every point of space-time. And so that's really the fiber bundle in its final form, and that's 1929. That was perfected by Yang and Mills. Well, it was extended to work not with a U1 group, which had replaced the R1 here, but Yang and Mills did it for an SU2, but in fact, it meant that one could do it for any non-abelian group as well, Lie group as well. And that is what we have now, the standard model, which was sort of completed in 1975, and I'll discuss that in more detail, is entirely based, it's really a direct line from here. At the same time, you have Albert Einstein trying from 1922 to add an anti-symmetric piece into his metric. That doesn't work, but that's what we call now supersymmetry. What he missed was that in order for the thing to be anti-symmetrized, you need fermionic behavior. And so you need to have a system that has, if you think of a space, the space has to be both commutative and anti-commutative. The two pieces have to be there. So supersymmetry fulfills precisely what he wanted to do with adding this anti-symmetric piece into the metric. So we have supersymmetry, and from there supergravity now. And the third possibility is adding dimensions. Kaluza and Klein, Theodor Kaluza and Oscar Klein, they made the suggestion at the time that to have electromagnetism, you need a fifth dimension. String theory and supergravity, in fact, all these modern developments now, all of them are based on taking that approach seriously, adding not one dimension, but in fact things are happening now in the latest version, which is known under the name, the mysterious name of M theory. M for matrices, M for whatever else you can think of as M, but or for membrane and so forth. So in M theory, you are in 11 dimensions, plus another 16 fermionic spinorial dimensions. So, and that's the approach. Incidentally, and this is something, we owe in this country, it's something I learned last year in trying to see what had happened in physics in Israel from the beginning. I looked up where we had started, and the first physicist in modern times in Israel, Sambursky, took his PhD under Kaluza and came straight to Jerusalem from the PhD under Kaluza. So in a sense, we owe Kaluza on top of that in the genealogy of teaching, we owe him something too. I come now to the other aspect, which is the one that is related to Pythagoras and to music. How did that get in the 20th century? Well, why did the Pythagoreans have this kind of approach? These are these simple relationships, like 1 to 2 to 3 to 4, etc., and they derive them from musical harmonics. They learned that dimensionless numbers are something that you can expect to behave simply. The moment you don't depend on a choice of a metric system or something else, you depend on nature, and then you can hope to have some simple relations appearing. Now, why did it happen in physics? In physics, because in music, because music, to a certain extent, if you want to look at music from our point of view now, it's an artificial spectroscopy. You don't have energy levels that in spectroscopy you have nature fixing the energy levels. In music, you have the boundary conditions fixing them of the instrument, or in fact the human ear having made a certain choice at some point. But from that point on, you have really harmonics, and you work out something that looks very much like what we have been doing in spectroscopy. Now, there was a false start, two false starts, to trying to work out that thing too early. Kepler's first model, you remember Kepler was very excited when he thought that he could get the distances of the planets by thinking of the five perfect bodies, cube, the tetrahedron, etc., embedding them one into another like Russian babushka arrangement, and in that way have the distances to the planets. It turned out to be wrong, although he was very excited about it, probably much more excited than about the regularities that he found, which were correct, the correct regularities, Kepler's laws. But it was a false start there. Eddington tried also to do something of that nature when he was trying to get from simple ideas, even the 137, if in mathematics you don't know that 137 is a very important number in physics. The charge of the electron in natural units comes out to be, it's really the charge squared, alpha square over 4 pi, E square over 4 pi h bar c, which is alpha. That is 1 over 137. Eddington thought that that was precisely so. Nowadays we know that it's a changing number and it's not very precisely 1 over 137. But he tried to find 137, and if somebody asked me in the question period, I can tell many stories about 137. Now, you needed tools to deal with these things properly. On the mathematics side, you needed Fourier analysis, you needed group theory, group representation theory, because, in fact, like a Plancherel formula, you had to go beyond the Fourier, very simple things of music. And then you needed tools in physics. The theorems of Emin-Netter were essential because the way nature presents us with these, the hint that we get from nature about the symmetries that will give afterwards this kind of analysis, and these groups come from conservation laws, and that's because Emin-Netter, thanks to the fact that Emin-Netter connected invariance principles and conservation laws. So because of that, that was necessary. All the results that we have in the second phase of geometrization, and which depend all of them on the musicalization first, they all come from thanks to the fact that this connection was made clear, was clarified. If it's a local invariance group, she said, or she showed, it would be, in fact, geometry, because you have a connection in that case appearing. You need parallel transport in a curved system, and then you need a connection. So what nature did was to supply us in the 20th century with phenomena that correspond to spectroscopies that have levels, system of levels. From that you could get a pattern, understand the order, and then understand the structure and the dynamics. But in fact, at this point here, you could already start working in the direction of that Pythagoras was advising us to do too. When I say that happened in the 20th century, we have in the 20th century this flood of spectroscopy. It started at the end of the 19th century. You see 1885, the Balmer formula in atomic hydrogen, looking at these numbers. Finding a formula, and then just using these. I think I missed the squares here too. That's same squares, yes. So you have these spectroscopies from which Niels Bohr got a structural model, and then you needed quantum mechanics to understand them. And the full picture using algebra was done by Wigner and Rakach, using full use of Lie group theory. I remember Rakach telling me that he had even found an application for G2, one of Cartan's 5 exceptionals in the F shell in atoms. So nature decided that music or spectroscopy was relevant because of really quantization. That's how it entered. Once quantization entered, then it became natural to have quantum numbers and to be able to have simple relationships the way Pythagoras was advising us to. In nuclei, the same thing was done in the shell model by Jensen and Maria Goeppert-Meyer. In hadrons, it was my luck to be able to make some of these contributions. I have a personal thought that came to me only in preparing this lecture. My name is Yuval, which in the Bible is the name of the first musician. That's in the 4th chapter of Genesis. I was a disappointment to my parents. They selected that name because they loved music, and I didn't do any music. In fact, I fled from the piano lessons that they tried to impose on me at the age of 5. And now, perhaps, had they been alive, I would have told them, I've been doing music all my life. So you have the hadrons, where we've been using SU3, etc., and all of that is in the same spirit. So that was an interlude between the first geometrization, the one that related to relativity, and the second one, which could start now once all of that was understood in terms of harmonics, or instead in terms of groups and representations, which are these Pythagorean type results. Then now one could go back to geometrization and have a second phase, which is called finally the standard model, which is, in fact, the standard model is a fiber bundle with a gauge group, which is a combination of U3 and U2 with taking a certain trace in the product. I mean, they are correlated. The U1 that is inside this and the SU2 and the SU3 that is here have a certain correlation. Now again, it was all done by nature. It began to look, in fact, in the weak interactions. In 1955, 56, parity, the non-conservation of parity was discovered, but that was thought at the time to be the great discovery. But that happened when nature was given a chance of voting between 5 possible Dirac bilinears. You take two Dirac spinors. You can make from them 5 different bilinears: scalar, pseudoscalar, vector, axial vector, and tensor. And everybody thought that nature was going to pick on scalar and pseudoscalar or something of that nature. It turned out that only vector and axial vector were selected by nature in the experiments. And the combination turned out to be really 2 vectors, in fact, with chirals. It's really the way the Lorentz group splits into 2, call them SU2s, it's these 2 chiral subgroups that appear here. And so, in fact, it was really, as a result of that, it meant that there is a vector current, or an axial vector current. A current carries a charge. A charge is quantized, turned out. And you could get, via Eminator, you could know which is the group. And so, first the weak interaction decided to show that it corresponded to some kind of symmetry. Then in measuring the electromagnetic form factors, that's again around 56. This is not me, this is Yoichiro Nambu. Yoichiro is also a first son, Yoichiro in Japanese, and Nambu, and so we have the same initials, YN, and he looked at the results of these electromagnetic form factor experiments that had been done by Hofstadter at Stanford, and which were very confusing because everybody had expected, since Yukawa had the idea of the meson, and the mesons had been discovered, that a proton and a neutron would be surrounded by a meson cloud, quantum emitted and quantum reabsorbed all the time. instead of a cloud of mesons, there was some kind of resonance. And the resonance, Nambu said, corresponds simply to the fact that it's not really a cloud of mesons, it's a vector meson at that mass. And it turned out to be correct. It could be produced in production experiments. And we started having the strong interaction also indicating that it was really a gauge theory of the Yang-Mills type. Then we enlarged the symmetry to SU3. And in doing that, there were paradoxes that nature prepared for us in order to be able to go on. One was, there was a spin statistics paradox, because to make a hadron, we found that we could make them from what Murray called quarks. That means a triplet representation, the fundamental representation of SU3, with 1/3 the barrier number and charges 2/3 and 1/3, and the proton would be two up quarks and one down quark, and the neutron would be one up quark and two down quarks. The problem was that quarks should have spin half if three of them make a particle which has spin half. So they have to be fermions by the spin statistics correspondence. And on the other hand, they arranged themselves in representations which were totally symmetric instead of totally antisymmetric. So it was very confusing. For instance, there is a famous resonance, the first well-known resonance was discovered by Fermi, which was called the 3-3 resonance, because it had spin 3/2 and isospin 3/2, made of three quarks, so you have to put them really in line symmetrically, so that they add up from 3 spin halves, to make one particle with 3.5 units of spin, and the same with isospin. So there must be something else antisymmetric if you want the spin statistics theorem to be correct, and the spin statistics theorem was proved if you assume a CPT, not more than that. So as a result of that, Nambu and Hahn and Greenberg made the first suggestion that perhaps there is one more SU3. Call our SU3 hadron, then there is another SU3 which was called SU3 color, in which they would be antisymmetric. That is really the group that is being engaged in quantum chromodynamics for the strong interaction, the force between the quarks, the strong force between the quarks. And it was also a Yang-Mills force. So you see, this is Yang-Mills force, the weak interaction of Yang-Mills force. Everything turned out to be of that type. There was still some additional effort in order to identify precisely the group that worked in the weak interaction gauge symmetry, which is an SU2 cross U1, or in fact a U2 that works together, with symmetry breakdown, spontaneous symmetry breakdown. Now, spontaneous symmetry breakdown was really introduced into particle physics by taking the Landau and Landau-Ginzburg ideas for phase transitions and adapting them to fields in particle physics. And so that was called the Higgs field or Higgs-Kibble field, and many people contributed to that at the time. So you have a symmetry and you break it in some direction. That is one way of looking at these things. Our colleague here, Alain Cohn, showed that if you take non-commutative geometry, you can reproduce them, or in fact, they become a superconnection à la Quillen, if you want to, or reproduce precisely. What he did was to reproduce precisely the Weinberg-Salam theory. That's Abdus Salam and Steven Weinberg. And to reproduce precisely the same theory without breaking the symmetry, by putting in, instead of having the symmetry broken, having the base space of the bundle be a discretized kind of base space made of two pieces in this case. So that's again adding to geometry. So finally we have a standard model, which is what I called phase 2 of the geometrization, which is a fiber bundle with this gauge group, and we finished the century with a theory which is everything we know is geometrical. That means all the forces that we know are described geometrically. In the last quarter of century, we have been trying to go beyond that, and that's where string theory comes in. Now, I bet with some people that finally string theory, whatever it will be also geometrical. That's not hard, I mean, an extrapolation from the past. But we have now something that affects the geometry, because that's quantum gravity, which would affect space-time. That is still missing when I drew a picture in which there is a phase one in which gravity is a geometrical theory, but it's classical. All the other forces make up a geometrical theory which is quantized. What is still missing to have a unified theory is you have to quantize gravity and have a unified theory. That is done now in two theories. Well, part of that is done depending on which theory it is. In string theory, you have both a quantization of gravity and also a unification. But you have a Kaluza-Klein situation in which you have to work in, as I said before, in 11 dimensions, 11 commutative dimensions and 16 anti-commuting dimensions. That's before quantization. Afterwards, it becomes more complicated. But that's to start with where things happen, the arena. The other possibility is to work with Hamiltonian Einstein theory. That means you take general relativity as is, and you treat it. Dirac made that suggestion that you quantize by finding what are the P's and the Q's, and then assuming Heisenberg commutation relations instead of the Poisson brackets and so forth. And so working in that method, since 1987, Ashtekar made suggestions with respect to the choice of representation of what kind of fields to take in Einstein's theory, and that seems to have been a success. It works to the point of having now, there is a quantum gravity of that type. It's not as well understood as the other cases because it's not a Fock space. You don't have one graviton, two gravitons, and so forth. You have something which is more like an instanton. That means or a soliton, a solution, which is a quantum solution. And that corresponds, in fact, to the representation is really the loop representation, which you can already find in Hermann Weyl, which we call Wilson loops in particle physics, but which Weyl already had, which is the integral over a contour of the fields, the field strength. And that is, you have, there is a quantization that works, and that's in Einstein's theory without having anything else. So in a way it looks, to start with, it may look like a contradiction that one theory requires all the other interactions to be there and more than that, in fact, because there's room for a lot. And whereas in the Ashtekar approach, you have pure gravity. But it may still be so that when there is a collapse of the extra dimensions, and you stay with 4 dimensions, you stay with the ordinary gravity, and the Ashtekar theory would be there. Let me say that in that folding up of the extra dimensions, which used to be was only talked about but not done in the Kaluza-Klein time in the 20s, it has been done in very great detail in the last 10 or 15 years in particle physics. That was one of the pushes of Witten at the time, and in fact the solution to this in the case of 11 dimensions was found by Freund and Rubin. It's a in fact, it even explains why, from 11-dimensional supergravity, why space-time has 4 dimensions. Because in 11 dimensions, gravity requires an additional piece in which the potential has 3 indices, is a tensor with 3 indices. The field strength has 4 indices. And the simplest solution to that field strength is that it's an epsilon 1, 2, 3, 4, or epsilon mu nu rho sigma, or a 4-dimensional epsilon of antisymmetric tensor for space. So it closes the rest of the dimensions into a 7th sphere and leaves open the 4 dimensions of space-time. Now, the 7th sphere immediately can make your eyes bubble out, because what don't you have in the 7 spheres? You can have, in the internal degrees of freedom, you have the Hopf vibration, you can have Cayley numbers, you can have the Hurwitz division algebras, octonions, anything goes there. So there are prospects for a lot of fun for whoever likes this kind of thing in mathematics coming out of that. When I'm asked what are the problems with string theory, or should one look at it as really the theory of the future or not? Of course, nobody knows, but I would say that today's lecture by Professor Frohlich may change my mind about the situation, and I'll explain why. He made the comment that there's no point in studying the limit to go from relativistic to non-relativistic, or from quantum to classical by taking h bar to 0, by taking h to 0, because the real thing in nature is that nevertheless we have classical situations appearing in other ways. My criticism to string theory was of that type. That means string theory contains, there is a simple limit of the kind of like h go to 0 to go to field theory. But there is no such limit to go to general relativity. And that I consider to be very ugly in string theory. General relativity comes out with a lot of pain and an expansion, and you have to, finally you take the first term in the expansion or so. But it's not something that naturally you go to in that limit. But if that limit is really not important, the limit like h go to 0, and you have to think, then maybe in that case, we can really live without that limit, and because we do get to general relativity within string theory. It's only that we get to it in an ugly fashion by long calculation, and not by that kind of natural thing. My previous comments used to be that it's not elegant enough to be a final theory, or a theory containing everything else. There's a lack of some kind of general principle, something nice. That still stays. But on the other hand, it contains elements that seem to answer all actual needs. It may have too much of them. I mean, that would be the question of where are all the groups that are contained in all these additional dimensions and so forth. There's too much room for lots of things there. But it certainly, with a certain amount of if you don't stick to only to beautiful results, simple results which correspond like getting to Galilean physics from Einsteinian physics by taking c to infinity. If you don't look for such limits, then you take away one of the only criticisms that you can have against string theory. So maybe it is going to be the theory of the future. Looking into the past was very much easier than trying to think of the future. I believe that a lot of interesting physics still exists in the future. It's not the end of physics the way that there was, I think, Hawking's inaugural talk was, the title was The End of Physics. And Steve Weinberg was more careful. He called his book Prospects of a Final Theory or something, or Dreams of a Final Theory. I believe in the opposite. That means that it'll go on and give jobs for physicists for a long time, because we are what string theory is giving us is already the behavior around Planck length and Planck mass and Planck energy, which is length of 10 to the minus 33 of a centimeter. And there, geometry becomes quantized. There may be room for non-commutative geometry. There probably is room for that kind of thing. It comes out also of the string formalism and so forth. So we have the quantization of geometry, but the final the final picture is that it's simply a change of physics, and then we'll have things going on above or below that length or above that energy, perhaps still going on. So then there'll be another conference for that thing. Thank you.
Thank you, Yuval, for a very beautiful presentation. Are there one or two questions? Yes? Why should negative be quantized?
Why should what?
Negative be quantized.
There was a suggestion. First of all, let me refer you. There is a paper of mine in the Annalen der Physik, the German publication, say quantum gravity. Hasn't it been done? And I count 8 ways in which the question could have been answered. That means one of the answers could have been gravity is not a quantum theory. Leon Rosenfeld used to think that way in the beginning. That's the Rosenfeld of Bohr and Rosenfeld. He thought that would give, in fact, it had the advantage in the Copenhagen interpretation of quantum mechanics, you need a classical background for the instrument that make the measurement. And so he thought that gravity might still be part of that background in that sense. But then you show easily that you can very easily, I don't know how do you call it, overturn or do things to the uncertainty principle. Because all you have to do is, we know that the planet Neptune was found by Le Verrier by some gravitational irregularities of Uranus, or I think something like that. So I mean, you can measure the position using gravity. You can also measure energy and momentum, and so you contradict Heisenberg commutation relations. So nature should not accept contradictions. That's the idea.
So I would like to ask about this question you raised about Columbus.
Yes.
Do you feel it's important that scientists justify what they do at the purest of science, mathematics and theoretical physics, by finding practical application?
No, I don't. And I think that shows how much nonsense can go into this kind of thing, and why judgment based on this shouldn't work. Incidentally, my answer, I think, it's of course easy to do it from that distance. My answer, if I would have been a professor in Salamanca, I would have said the following. If Columbus is right, then obviously there's all this money to be earned, and that's so forth. But I think it's nonsense, and he's wrong. But if he's wrong, then it means that the Earth is much larger, and it means that there are about 20% of the area of the Earth that we don't know nothing about. These 20% could contain new oceans, new continents, whatever. For that purpose, we recommend the exploration. So it's easier to do now, but I think that's the approach that should go. That means anything where you explore the unknown is worth doing, because you never know where the results are going to come from.
They would die.
Yeah.
If not for America, they would die.
I beg pardon?
If not for America, they would die. Yeah, they would.
Yes, of course.
They would die because not enough supplies.
And then they would
Yeah.
that
So
would
you would
come.
have written a positive recommendation anyway. Let
Well,
him die.
no, I would say, I would say if he believes, then it's his business from that point of view. Yes.
Well, I think we have a great deal to talk about in the break, and we'll come back in 10 minutes to hear Elad Khan. Thank you.